In this lecture, we develop a step-by-step introduction to matrix quantum gravity through the framework of the BFSS model, which is a matrix quantum mechanics, and its connection to the black zero-brane of type 2a supergravity, which is a black hole in higher dimensions. We begin by recalling the Feynman path integral formulation of quantum mechanics, emphasizing how quantum amplitudes can be represented as sums over all possible trajectories. From there, we introduce the idea of dimensional reduction, showing how adding or removing extra dimensions leads naturally to matrix models, where the degrees of freedom become matrices instead of scalar coordinates. Next, we position this construction within the broader context of the gauge-gravity duality. We explain how the BFSS model arises from 10-dimensional supersymmetric Yang-Mills theory, and how its large N, strong coupling limit is dual to a gravitational background. The black zero-brane, providing a concrete, testable realization of M-theory in a quantum mechanical setting. We then discuss the structure of supersymmetric Yang-Mills quantum mechanics, showing how all BFSS and BMN systems emerge from the requirement of maximal supersymmetry and how this connects different matrix models across dimensions. Afterward, we turn to the lattice formulation, where we address gauge symmetry and gauge fixing, ensuring unitarity and gauge invariance at every step. We then explore chiral symmetry and the problem of fermion doubling, introducing the Dirac-Wilson operator and showing, in the simpler case of BFSS3, how the Wilson term removes unphysical fermionic modes while preserving gauge covariance, a mechanism that generalizes to all higher dimensional matrix models. With the theoretical framework established, we describe the rational hybrid Monte Carlo algorithm, the numerical engine that allows us to simulate the full supersymmetric BFSS model non-perturbatively. Finally, we apply this machinery to the study of black hole physics, in particular, Hawking radiation, as a direct test and verification of the gauge-gravity duality. Through this synthesis, we see how matrix quantum mechanics not only reproduces the thermodynamics of the black zero-brane, but also reveals the microscopic quantum mechanical mechanism of black hole evaporation. Quantum mechanics can be expressed as a sum over all possible trajectories. Each path contributes a complex phase, e to the is over h bar, and the interference of these phases replaces the determinism of classical motion. To make this integral mathematically meaningful, we perform a Wick rotation, replacing real-time t with imaginary time tau. The path integral then becomes exponentially damped, turning quantum mechanics into a statistical ensemble in imaginary time. The Euclidean path integral, with periodic boundary conditions, is in fact identical to a thermal partition function. The periodicity of imaginary time defines the inverse temperature, beta equals 1 over t. Expectation values computed in this ensemble correspond to thermal averages, forming a direct link between quantum fluctuations and finite temperature physics. To evaluate this path integral numerically, we discretize imaginary time into a lattice of lambda points separated by spacing a. This converts the continuum action into a finite sum that can be simulated on a computer. Quantum configurations are then generated using the Metropolis algorithm, accepting or rejecting updates with probability proportional to e to the minus delta s over h bar. Iterating this process yields a representative ensemble of quantum paths, making the theory computable from first principles. We now take a conceptual leap. We replace the single coordinate q of t with an n by n Hermitian matrix, m of t. The action becomes the trace of kinetic and potential terms involving m. This generalization elevates one particle into a system of n-squared interacting degrees of freedom, a miniature universe governed by matrix dynamics. This simple step is the starting point of matrix quantum mechanics, the seed of the BFSS model, and the foundation of matrix quantum gravity, where space-time and gravity emerge from the collective behavior of matrices. The BFSS matrix model originates from 10-dimensional supersymmetric Yang-Mills theory, which itself is the low-energy limit of open superstring theory. The core idea is to perform a dimensional reduction of this 10-dimensional theory down to a single time dimension. All spatial dependence is removed, and the gauge fields that originally depended on space become time-dependent matrices. After reduction, the spatial gauge fields AI become 9 Hermitian matrices, denoted XM of T. These matrices describe the collective coordinates of ND zero-branes, which are point-like objects in string theory carrying mass and charge. The 10-dimensional Majorana-Weil spinor reduces to 16 real fermionic degrees of freedom, maintaining maximal supersymmetry, that is, 16 supercharges in 0 plus 1 dimensions. The resulting theory is a supersymmetric matrix quantum mechanics, whose action is written in equation 1. It contains the kinetic term for the matrices, a commutator-squared potential that encodes their interactions, and the fermionic terms coupling the matrices to the spinor fields. The commutator-squared term, 1/4 times the trace of bracket xm, xn squared, captures the non-abelian interactions between d0-branes, in essence, their quantum gravitational binding. Physically, the BFSS model describes the full quantum dynamics of ND0-branes. In the large N limit, it is conjectured to provide a non-perturbative definition of M-theory formulated in the discrete light cone quantization frame. This makes the BFSS model the prototype for matrix quantum gravity, a theory in which space, time, and gravity emerge from the collective behavior of matrices. The gauge-gravity duality, also known as the Maldacena correspondence, is one of the deepest ideas in theoretical physics. It states that a strongly coupled supersymmetric gauge theory can be equivalently described by a weakly coupled gravitational theory in higher dimensions. In other words, gauge fields living on a lower dimensional boundary can fully reproduce the dynamics of gravity in a higher dimensional bulk. To understand where this comes from, recall that a stack of n-coincident dp branes supports open strings whose low-energy limit is a p+1 dimensional supersymmetric UN-Yang-Mills theory. At the same time, those same dp branes curve spacetime, sourcing a black dp brane geometry in type 2 supergravity. Thus, the open string description on the branes and the closed string description in the bulk are two sides of the same physics. The correspondence can be written schematically as supersymmetric p+1 dimensional UN-Yang-Mills theory is dual to type 2 superstring theory on a black dp brane background. For the special case p equals 0, this relation reduces precisely to the BFSS matrix model and its gravitational dual, the black zero-brane. This is the concrete example in which quantum gravity emerges from the dynamics of matrices. The BFSS-10 model, matrix quantum mechanics with 9 bosonic matrices and 16 supercharges, describes the dynamics of ND0 branes in M-theory. But this construction can be generalized by reducing the number of spatial matrices, leading to a family of lower-dimensional matrix models denoted BFSSD+1. Each of these represents a maximally supersymmetric quantum mechanics in d-spatial directions. The supersymmetry algebra imposes strong constraints on which values of d are allowed. Consistent closure occurs only for d equals 2, 3, 5, and 9, yielding models with 2, 4, 8, and 16 real supercharges respectively. These correspond to effective matrix quantum mechanics obtained from higher dimensional super-Yang-Mills theories compactified to a single time dimension. Each BFSSD+1 model also has a dual gravity interpretation. It is holographically equivalent to superstring theory on a black zero-brane background in a spacetime of dimension d sub ym equals d+1. Adding a supersymmetric mass deformation produces the BMN d+1 models, which correspond to pp wave geometries in M-theory and contain half BPS bubbling vacua. Altogether, these generalizations show how matrix models, pp wave backgrounds, and black brane geometries are connected within a single M-theoretic framework, providing a unified picture of matrix quantum gravity across dimensions. To study the BFSS model non-perturbatively, we place it on a Euclidean time lattice, where time is discretized but gauge invariance is fully preserved. This allows us to simulate the dynamics of matrices numerically while keeping the fundamental local symmetry intact. The bosonic matrices, denoted xm of t, are parallel transported between lattice sites by link variables, written un n+1 equals e to the minus I a t of n. These links ensure gauge covariance under local transformations. To remove redundant degrees of freedom, we fix the gauge by choosing the Polyakov, or static diagonal gauge, in which all temporal links are concentrated in the final link of the lattice. The remaining information is encoded in the holonomy D, a diagonal matrix of phases e to the I theta sub I. After gauge fixing, the path integral measure reduces to the eigenvalue angles theta sub I, accompanied by a Vandermonde term, the Faddeev-Popov determinant, proportional to the product over I less than j of sine squared of theta I minus theta j over 2. This determinant captures the residual interactions among the holonomy eigenvalues even after gauge fixing. Physically, this gauge-fixed lattice action provides a finite temperature gauge-invariant discretization of the BFSS model. The eigenvalues of the holonomy act as an order parameter distinguishing the confinement-deconfinement transition, which, in the dual gravity picture, corresponds to the formation or evaporation of a black hole. On a discrete lattice, naive discretization of derivatives leads to a well-known artifact called fermion doubling, the appearance of extra unphysical fermion species. This problem must be resolved to recover the correct continuum spectrum of the BFSS model. Here, we focus on BFSS3 for concreteness, but the fermion doubling problem and its Wilson term solution apply in the same way to all higher BFSS D+1 models. In one dimension, the issue arises because the antisymmetric difference operator introduces two light modes in momentum space, one near p equals 0 and another near p equals pi. To remove this unwanted pi mode, we add a Wilson term, which acts as a momentum-dependent mass. This term opens a large gap for the doubler while leaving the physical branch unaffected. The corrected derivative is called the Dirac-Wilson operator. It consists of gauge covariant forward and backward derivatives, denoted d plus and d minus, built from the lattice holonomy. The full operator is represented as a block matrix with off-diagonal entries d tilde plus and d tilde minus, each of which contains the Wilson correction proportional to the lattice spacing times the Laplacian. This procedure, known as Wilson improvement, eliminates the extra fermionic modes while maintaining gauge covariance and locality. As a result, we recover a single light fermion species in the continuum limit, ensuring a consistent, supersymmetric, and gauge-invariant lattice formulation of the BFSS3 model. To simulate the full supersymmetric BFSS matrix model non-perturbatively, we employ the rational hybrid Monte Carlo algorithm, or RHMC for short. This method is gauge covariant, ergodic, and numerically stable, allowing us to explore the true quantum dynamics of the model while correctly incorporating the effects of fermions through pseudo-fermion fields. The procedure begins by integrating out the Grassmann variables in the path integral. This produces a Pfaffian, written as Pf of m, where m is the fermionic operator. The modulus of the Pfaffian can be expressed as the determinant of delta to the 1/4, with delta equal to m dagger times m. To handle this determinant numerically, we introduce complex pseudo-fermion fields, denoted xi, so that the fermion determinant becomes an ordinary Gaussian integral over these auxiliary fields, weighted by e to the minus xi dagger delta to the power minus 1/4 xi. The fractional power of delta, namely delta to the minus 1/4, is computed using a rational approximation implemented through the Rumez algorithm. The resulting linear systems are then solved efficiently using multi-mass conjugate gradient solvers, which allow simultaneous inversion for all coefficients in the rational expansion. The molecular dynamics evolution proceeds by defining an effective Hamiltonian that includes kinetic terms for the bosonic and holonomic momenta, together with the effective action S effective of x, theta, and xi. Hamilton's equations are integrated using a leapfrog scheme, generating trajectories through configuration space. During each trajectory, the pseudo-fermion field is kept fixed. Each trajectory is then subject to a metropolis accept-reject test, followed by heat bath refreshment of the momenta, and when required, the pseudo-fermion fields. This combination of rational approximation, molecular dynamics, and metropolis updating forms the backbone of the RHMC algorithm, the key tool enabling controlled, gauge-invariant Monte Carlo studies of the supersymmetric BFSS model at finite temperature and finite n. BFSS-10, the supersymmetric UN matrix quantum mechanics of ND zero-branes, is dual at large n and strong coupling to the black zero-brane of type 2a supergravity, obtained by reducing the 11-dimensional M-wave. This gives a concrete, testable realization of the gauge gravity duality. Near the horizon, black-brane thermodynamics predicts the energy density given in equation 3. The first term is classical supergravity. The 1 over n squared term encodes the one loop, r to the fourth correction from string M theory. Lattice BFSS Monte Carlo reproduces both scalings. Because of flat directions, D0 branes can escape the bound state, the matrix model manifestation of Hawking radiation. At large n, the bound state is stable, a classical black hole. At finite n, the state becomes metastable and evaporates, a quantum black hole. The quantitative match between matrix quantum mechanics and black-brane gravity at both leading and subleading orders provides a sharp, non-perturbative test of quantum gravity in this sector. In sum, we have moved from the path integral to matrix quantum mechanics via dimensional reduction, placed BFSS within gauge gravity duality as the dual of the black zero-brane, and built a lattice plus RHMC framework that treats gauge and fermion issues correctly. We then used this machinery to probe Hawking radiation, turning the BFSS model into a quantitative test and prediction of quantum gravity.